picture this for a second, right? You're sitting in a dimly lit room.
Oh yeah, classic clinical setup.
Exactly. And you're just staring at a high-definition monitor. The screen is glowing with these pinkish, highly textured images of tissue, and it's all moving in real time.
Just hours and hours of that.
Right. You do this for hours. And this is the physical reality for a gastroenterologist performing routine endoscopies and colonoscopies.
It is. And it's intense work.
It really is. And at some point, you, the listener, or someone you love, will likely need one of these screenings. They are our absolute best primary tool for catching gastrointestinal cancers early.
Absolutely vital.
But, I mean, the human bottleneck here is fatigue. Staring at those screens, processing the vascular patterns of the mucosal surface for hours on end, it is exhausting.
Oh, completely exhausting. It's an environment where a tiny lapse in visual attention or simply just the cognitive load of a 12-hour shift, it directly impacts patient outcomes. I mean, a missed flat adenoma today becomes a severe malignancy down the line.
Exactly. So naturally, the medical field has spent the last decade trying to bring artificial intelligence into the room, to act as a second pair of eyes.
Which makes sense.
But today's mission is a deep dive into a completely different kind of AI. We are looking at a really fascinating new research paper titled Analogical Reasoning as a Doctor, a foundation model for gastrointestinal endoscopy diagnosis.
It's a bit of a mouthful, but it's a great paper.
It is. And this is from experts at Shanghai Jiao Tong University, along with a whole coalition of medical institutions. And we have a massive stack of their visual clinical data to unpack today.
So much data.
Yeah. Whether you are a tech enthusiast, a clinician, or just someone who wants to understand what the future of your own medical care looks like, this deep dive is going to show you how AI is evolving.
It really is a massive shift.
It is. We are moving away from the AI that acts as a rigid brute force calculator and moving toward a model called RTNet. That's Relevance-knowledge acquisition and transfer network.
Right, RTNet.
And this model actually mimics human cognition.
Yeah, and to really appreciate what a model like R8net achieves, we have to look at the structural failures of the medical AI that came before it. Right.
That's true.
Because current models suffer from this crippling vulnerability called domain shift.
Domain shift, right.
Yeah, and that's compounded by a really severe scarcity of high-quality, standardized medical data.
Okay, let's unpack this domain shift problem because the source data has a glaring example of this.
It really does.
The researchers looked at a very powerful existing AI model called GastroNet. Now, GastroNet was trained on, 5 million endoscopic images?
5 million, yeah, that's a huge number.
You would think 5 million images of human tissue would make it an absolute genius.
Right, you'd assume so.
It was trained on images captured by the 3 major endoscope manufacturers, Olympus, Pentax, and Fujifilm.
Exactly.
But then, the researchers took this supposedly genius AI and tested it on a completely different dataset called PolypGen.
Yeah, and PolypGen consists solely of images captured with Olympus equipment.
Just Olympus.
And what happened? The AI failed.
It just collapsed.
Completely, because the overall statistical distribution of the test data shifted away from that mixed brain environment it was used to.
Oh, wow.
Yeah, GastroNet couldn't prioritize the Olympus knowledge it already possessed. It couldn't, adapt to the specific domain it was currently operating in.
That is wild.
The AI essentially learns the noise, right? The specific color calibration, the lighting quirks of its exact training set.
Right, the background details.
Exactly. So when you remove the Pentax and Fujifilm data, the statistical distribution of the pixels is suddenly foreign to the model, and its reliability just collapses.
Like someone who learned to drive a Honda Civic in a quiet, perfectly mapped out suburb,
Oh, that's a good way to put it.
They know the rules. But then you drop them into the driver's seat of a massive double-decker bus in the middle of a chaotic London roundabout.
They'd have no idea what to do.
Exactly. The rigid rules they memorize no longer apply, and they crash.
Right.
And the data shows this problem gets exponentially worse when you introduce label heterogeneity.
Oh, the label heterogeneity. That is a nightmare.
Because doctors and hospitals don't all speak the exact same language when they're annotating these images, do they?
Not at all. I mean, you have different hospitals calling the exact same visual anomaly by completely different names.
Right.
Or they're using entirely different scoring systems to grade severity.
Right.
Like one data set relies on the Mayo endoscopic score.
Okay, and that grades bowel inflammation on a scale from 0 to 3. Right?
Exactly, 0 to 3. But another hospital might use the Boston Bowel Preparation Scale, or BBPS.
Oh boy.
Yeah. If you feed both of these data sets into a traditional AI, the model's loss function, which is the math it uses to correct its own errors.
Right, the feedback loop.
Yeah, it goes completely haywire because the labels conflict.
It just gets confused.
It cannot mathematically reconcile why identical tissue damage is called a 3 in one folder and something completely different in another.
Which brings us to the core question, right? So how do we teach an AI to adapt to the London bus?
Yeah, exactly.
How do we build an AI that doesn't just memorize the pixels of the suburb, but actually understands the underlying concept of driving?
And this is where ArtNet introduces analogical reasoning.
Okay, analogical reasoning. Break that down for us.
Well, think about how human doctors diagnose a patient. They don't have millions of images perfectly memorized pixel by pixel in their heads.
No, of course not.
Right. They gather the visual cues, they generate a hypothesis, and they draw inferences from analogous past cases.
Like, oh, I've seen this before.
Exactly. They look at the vascular structure and say, this pattern behaves similarly to a case I saw 3 years ago.
And RATNet does this.
RATNet is engineered to replicate that exact cognitive process.
Wow.
It uses a cyclic pre-training strategy across 5 vastly different data sets to build a prior knowledge base.
Okay, a prior knowledge base.
Right. It takes a data set like 𝗤𝗡𝗏, which consists of pediatric colonoscopies from a children's hospital,
Okay.
and analyzes it alongside the 𝗤𝘯𝘢𝗫𝗃 data set, which is heavily focused on that Mayo inflammation score we talked about.
So it's looking at very different things at the same time.
Yes. RTET extracts the abstract fundamental patterns from all these different domains and maps them in a mathematical vector space.
So it's finding the underlying commonalities.
Exactly.
Then we get to the actual clinical application.
Right.
Because when RTET is presented with a brand new, unseen image from a patient's colonoscopy today, it estimates what the paper calls posterior knowledge from that single image.
Yes. Posterior knowledge.
And it scans its massive library of prior knowledge, computes the mathematical similarity in that vector space, and transfers the relevant insights to make a diagnostic inference.
That's the analogical reasoning in action.
It's like sitting down to play a brand new, highly complex board game, right?
Oh, I like this.
You open the box, and instead of spending 3 hours reading a 100-page rulebook from scratch,
Which nobody wants to do.
nobody wants to do that, you look at the board and realize, oh, this is basically just Monopoly, but set in space.
That is a perfect analogy.
You transfer your prior knowledge of the mechanics of Monopoly to this new domain. You know that rolling the dice moves your piece, even if the board looks totally different.
Exactly. And in this scenario, the rules are the underlying vascular patterns and tissue textures, while the space dollars are the hospital's specific labels. The space dollars.
Right. RATNet solves that label heterogeneity problem by utilizing a teacher-student architecture.
Okay, teacher-student.
Yeah, and it's equipped with multitask heads.
Heads. Like literal heads.
Well, in a neural network, a head is simply the final output layer trained for a specific task.
Got it.
So instead of forcing a single unified label system across all hospitals, which, as we know, destroys the nuance of the local
Or
data,
he messes everything up.
RATNet allows each data set to keep its native language. It has a dedicated head for the Mayo score and a separate head for the BBPS.
Okay, let's break down that teacher-student architecture mechanically.
Sure.
How is the AI learning the underlying pathology without mixing up the local terminology? Well, the student model is the part of the AI actively processing the new, messy data from a local hospital.
Okay.
It learns quickly, adapting to the specific labels of that facility.
Right.
But if we just relied on the student, it would forget its past training. It's a problem called catastrophic forgetting.
Catastrophic forgetting.
That sounds bad.
It is bad. To prevent this, R8net uses an exponential moving average to update the teacher model.
An exponential moving average.
Think of it as a mathematical dampener. It takes only a tiny fraction of the student's newly acquired weights and slowly integrates them into the teacher model.
Okay, so it's not overwhelming the teacher.
Exactly. The teacher maintains a stable, overarching understanding of what diseased tissue looks like universally, while the student handles the local translation.
So it's learning the concept of the disease, completely independent of the name tag.
You nailed it.
But, we need to look at the actual clinical results from the paper to see if this theory holds up under pressure.
Let's do it. The researchers put RATNet through 6 distinct clinical scenarios, and the zero-shot transfer tests are the most revealing.
Oh, absolutely.
And just to clarify, zero-shot meaning the AI is deployed completely blind into a new environment without any practice rounds or task-specific retraining, right?
Right, no safety net. They deployed RTNet to completely unseen data sets from new hospitals.
Wow.
Specifically that Olympus-only polyp-gen data set we discussed earlier, alongside a private data set from 𝗖𝗡𝗄 Hospital.
And RATNet had never seen these specific patient populations.
Never. It hadn't seen the specific lighting of this hospital's equipment or their annotation styles. Nothing.
And yet, it achieved an area under the curve, or AUC score, of 94.24% for detecting the most severe level of inflammation, Mayo 3.
That number is incredible.
An AUC of 100% is perfect classification. Hitting 94% on the dataset it has literally never seen before is staggering.
Especially when you consider that older foundation models like GastroNet and GastroHUN were scoring in the 30s and 40s in the exact same scenario.
30s and 40s, that's practically guessing.
Worse than guessing in some cases. They completely collapsed under the domain shift.
Right.
Those older models were brittle. RTNet survived the domain shift because of that analogical reasoning.
It didn't look for the specific pixel arrangement.
Exactly. It looked for the underlying structural analogy of severe inflammation.
But wait, I have to play devil's advocate here.
Go for it.
If the AI requires pattern recognition, how is it diagnosing a rare lesion like a serrated adenoma if there was zero data on it in the pre-training?
That's the big question.
Right. I mean, if a human doctor rarely sees a condition, an AI trained on human data rarely sees it either.
True.
If an AI needs 10,000 images to learn what a standard polyp looks like, diagnosing a hyperplastic lesion it has literally never encountered sounds like magic, not math.
And that is the critical vulnerability of traditional deep learning, right? It biases heavily toward the head of the data distribution, the most common diseases.
Yes.
But what's fascinating here is how few-shot learning changes the paradigm. Our RATNet only needed 1 to 5 sample images of these rare conditions to start accurately identifying them.
1 to 5 images.
Just 1 to 5.
That is insane. How?
Because our RATNet already possesses a deeply mapped latent space of healthy tissue and common anomalies.
Okay.
When you introduce one image of a rare serrated adenoma, the AI doesn't have to learn what human tissue is from scratch.
Oh, right. It already knows the basics.
Exactly. It plots that new lesion in its vector space relative to everything else it knows. It recognizes that the tissue structure is analogous to other known anomalies, just presenting with a slightly different morphological syntax.
So it maps the delta, the difference, rather than trying to memorize the entire image.
Yes, it just learns the difference.
And that dynamic is proven by the tests on the GastroVision dataset, right?
Oh, absolutely.
Because GastroVision contains 22 different classes of diseases, and many of them are incredibly rare. They represent the long tail of the data distribution.
Very long tail.
The researchers intentionally slashed the available training data down to just 5% of its original size to simulate extreme data scarcity.
Which is a brutal test.
Very brutal. But even starved of 95% of the information, R8Net maintained highly accurate diagnostic capabilities across all 22 classes.
It doesn't just focus on the easy, common stuff.
No.
The analogical reasoning allows the model to be highly data efficient. It extracts maximum conceptual value from a minimal amount of pixels.
Okay, so the AI can handle rare edge cases in the data, but what about an entirely different physical environment?
Oh, you mean the capsules?
Yes. The source is detailed tests on the 𝗤𝗄𝘅 capsule dataset.
This part is wild.
It is. Because this isn't a traditional endoscope on a tube. It's a literal pill camera you swallow.
A pill camera.
And the images look totally different. They are lower resolution, the lighting is totally inconsistent, and the camera is just tumbling uncontrolled past intestinal villi.
Yeah, the mucosal surface of the small intestine captured by a tumbling capsule looks fundamentally different from the colon walls captured by a high-definition endoscope.
It's a completely different visual domain.
It is a massive environmental shift.
Yet with just a small amount of incremental learning, RATNet hit an AUC of over 99% on this new modality.
99%.
Over 99. It adapted to the pill camera almost instantly because it didn't have to relearn the concept of a bleeding lesion.
Right.
It just transferred its prior knowledge to this new lighting and resolution environment.
It's beautiful, really.
It is. But this brings up the massive bottleneck of scaling this technology.
Yeah, the privacy issue.
Exactly. Because to build a superdoctor AI, you need patient images from thousands of hospitals all over the world.
Millions of images, ideally.
But hospitals cannot legally or ethically just email highly sensitive private medical records to a centralized server.
No, absolutely not. IPA and GDPR exist for a reason.
Right. The privacy laws prevent the aggregation of the very data the AI needs to get smarter.
And this is the exact hurdle that has stunted global medical collaboration for years.
So how do they solve it?
Well, the researchers address this by engineering Federated RATNet.
Federated RATNet.
Yeah. If we connect this to the bigger picture, traditional AI requires you to bring all the world's data to a central model. Federated learning brings the model to the data.
Okay, explain the mechanics of how that bypasses the privacy restrictions. Like, how does the central server learn if it never sees the images?
Okay, so the central server sends a blank or partially trained RATNet model out to the local hospital.
Okay, so the AI goes to the hospital.
Right. And the model lives securely on that hospital's own internal servers. It trains on the hospital's highly private patient data locally, computing the gradients.
The gradients being the mathematical adjustments it needs to make to improve its accuracy.
Exactly, the adjustments. The hospital does not send a single patient image back to the central server.
Not one.
Not one. It only transmits the updated mathematical weights.
Wow. It's sending back the math, not the pictures.
Just the math. The central server takes those abstract mathematical weights and averages them with the weights sent from hundreds of other hospitals around the world.
That is brilliant.
It is. The global model gets smarter by integrating the varied knowledge of every local facility, and then that newly updated, smarter global model is sent back out to all the participating hospitals.
So patient privacy is perfectly preserved because the actual pixels never left the local building.
Exactly.
So if we look at the whole picture here, we are looking at a model that learns from just a few examples, adapts to entirely new hospital equipment without retraining, deciphers tumbling pill cameras, and aggregates global medical knowledge without ever breaching patient privacy.
It really feels like the era of brute forcing massive, perfectly labeled data sets controlled by a single tech entity is ending.
Yeah.
The future of medical AI is in building open, cost-effective models that can actually reason, adapt, and learn from the messy, heterogeneous, real-world environments that human clinicians deal with every day.
So what does this all mean for you, the listener? That is the crucial takeaway here.
Right.
This technology democratizes expert-level diagnostics. It translates to fewer misdiagnoses, faster results, and a vastly higher standard of care, regardless of whether you are being treated at a multi-billion-dollar research hospital in a major city or a small, resource-limited rural clinic.
Absolutely. Because if that rural clinic has access to the Federated RATNet model, they essentially have the combined analogical reasoning of the world's best gastroenterologists analyzing their screens in real time.
It levels the playing field in global health.
It does, because the AI is no longer too brittle to survive outside of a sanitized laboratory environment.
Yeah, it acts as an equalizer, ensuring that the quality of diagnostic interpretation isn't dependent on the geographical location or the specific brand of camera a hospital can afford to purchase.
It's an incredible leap forward in how we handle physical pathology.
It really is. But it also leaves us with a really provocative thought to end on today.
Oh.
Yeah, because today we've been talking about objective physical realities. An ulcer, a polyp, inflamed tissue in the gastrointestinal tract.
Very tangible things.
Right. RATNet proved that an AI can successfully master human-like analogical reasoning to diagnose those objective realities from just a few examples.
It maps the mathematical analogy of the tissue.
Exactly. What happens when this exact same analogical reasoning framework is applied to highly subjective, culturally nuanced fields of medicine?
Oh, wow.
What happens when an AI built on this architecture is fed the data for psychiatry or complex, largely invisible autoimmune disorders?
That is a fascinating question.
If an AI can learn to reason through the muddy, subjective waters of the human mind, the way it maps the physical landscape of the digestive tract, how will our very definition of a medical expert change?
Yeah.
When the ultimate diagnostician isn't a single person with decades of localized experience, but an open-source, globally distributed reasoning network? Where does human intuition end and artificial reasoning begin?
That's heavy.
Something to mull over the next time you find yourself sitting in a dimly lit clinic, waiting for the results on the glowing screen.